I'm going to end off our little look at discrete probability distributions with this idea of what's called statistical inference. Okay, so statistical inference is where we then use the data we've collected to make predictions, basically. Now, we're inferring things rather than deducing things. So it's the difference between deduction and inference, because when you deduce something, it's coming from known facts. With stats, we can only infer because we haven't got all the data. We've only sampled certain pieces of the data. So for that reason, we call it inference. So what it assumes is that that sample of data that we've got, I can use to make predictions about the whole population. I don't have to talk to everybody. I can just pick a sample of the group to infer what I want to infer. So what exactly is sampling? Okay. So to sample, as I said, rather than speaking to the whole population, and depending on what we're talking about, that could be a rather large number of people or whatever it is we're surveying to do, we just take a sample, so a group of it. So why do it? Well, it's going to be quicker. Certainly going to be quicker than to talk to every possible person. It's going to be cheaper. Accuracy. This is a weird one. You'd think, hang on, it'd be the other way around. Surely if I had a larger group, my information would be more accurate. But it actually can be the reverse. Because when you're dealing with such big amount of data, then you've got more of a chance to make a mistake in there somewhere with the data. So actually sampling can tend to be more accurate than the whole population. Sounds weird, but that's the way it works. And of course, necessity. Sometimes it's just not possible to get every possible piece of data. The example I've got there are matches. Now, if you want to quality test matches to see if it's a good match, you can't physically light every match to see if they work. I mean, otherwise, you've then got no matches to sell because you've lit them all to see if it's any good. So that would be a necessity to sample out of the batch, to you test a few and go, yep, this batch seems to be okay, we can go and sell the rest. So sometimes necessity comes into it. All right, well, how should we get our samples? And it's always randomly. Okay? If you want to get a good sample, it should be random. So every element in our population, our sample space, has an equal chance of being selected. So that way there'll be no bias or predictability, because we want to make predictions from the sample. But what that does mean, though, is when you pull out a random sample, it may not necessarily be a cross-section of the whole population. It all depends where I draw my sample from. So if it's truly random and they come from everywhere, let's take the recent election, for example. And they like to do opinion polls and find out what people are thinking. So obviously you can't survey every person in the country, and so they sample. But if I don't get people from, say, the western suburbs of Sydney, then it might not be a good predictor about who's going to win the election. And as it turned out, I mean, if you've been reading the news over the last few weeks, in fact, those opinion polls that they had proved to be terrible. And that all came down to the sampling, the way they sampled. They weren't drawing good samples to get an accurate predictor of how the election was going to fall. So, all right, some notation and terminology. There's two collection methods. When we are collecting every piece of possible data, we call it a census. So a census captures every possible piece of data. The most common census you may have heard of is the Australian Bureau of Statistics. How often do they do it? 4 or 5 years? They go out and every household has to fill in the form, though last time we did it was online, but every household has to fill out a form about how many people live in the house, the ages of the people, all that sort of stuff that the Australian Bureau of Statistics then puts together so people can use that data for things. So that's a census, whereas if I'm just getting a sample, we call it a survey. So that's the difference between a census and a survey. Census aims to capture, I say aim because theoretically it captures every piece of data, but of course you are going to miss some. You know, there'll be someone who says, no, I'm not going to fill the form in or something like that. So you will miss some. But the aim of a census is to capture every piece of data. So then when we talk about probability of x equals x, as we saw, we talked about px. Well, really that notation is when you are talking about a population. When we're doing a sample, we call it relative frequency. And so the symbol is, f with a little r down the bottom to say relative frequency. So expected value, say the symbol for expected value, for a population the symbol for mean is mu, whereas for a sample it's x with a bar on top. Variance, sigma squared for the population, s squared for the sample. So you'll see those different notations. Now what we should see happening as n approaches infinity, so getting closer and closer to capturing every possible piece of data, then the x bar, so the sample mean, should approach the mean of the population. And similar with the variance, they should approach each other as well. So let's have a look at this one. I'm going to roll 2 dice, pretty common sort of thing we do in stats. Use the theoretical probability distribution. So the theoretical probability distribution would be like the census. Because theoretically we're going to say we could get every possible outcome and we know what the probabilities of those things would be. And we'll we'll calculate the expected value and the variance. Now, before I put this up, although you might have seen the answer already on this sheet, if I was to roll 2 dice, what would you expect the sum of the 2 dice to be? Well, obviously there's all sorts of things it could be. Could be 2, could be 3, could be 4, could be 5, could be, and so on up to, 12 would be the maximum, wouldn't it? So what would you expect it to be is the question. Let's have a look at it. So I've drawn up my frequency table. So there's x, all the possible outcomes, 2, 3, 4, 5, 6, 7, and so on. The probability of them happening. And I did this in a spreadsheet, and it's just showing 4 decimal places. But you can see the sum of the probabilities is 1, which is good. That's what we want it to be. The sum of the xpx would be our expected value. You can see the sum of that row is 7. You would expect the answer to be 7. Now, I don't know if you've ever noticed this with a die. Opposite faces on a die always add up to be 7. On a regular 6-sided one, I should say. And so there's my x squared px. The sum of that one turns out to be 54.833. So we should be able to work it out. Well, expected value, we know that's the sum of the xpx, so that's 7. Remember, the quicker way of finding variance, I reckon, is the expected value of x squared, which is what I've worked out on the 4th line there, minus the average or the expected value squared. So 54.83 repeater minus 49. So the variance is 5.83. The square root of variance is standard deviation. That makes more sense, because if our average is 7, we're saying, well, one deviation when we're talking about the spread is about 2.4 away from that. So that gets us to 9.4 on the higher end of the scale. 2 deviations from that would be about 4.8. So 7 and 4.8, what's that? 11.8. So we haven't quite captured all the data yet. Remember, we said with 3 deviations, we pretty much should capture all the data. If I was to graph it, that's what it would look like. Okay, so there's all the probabilities as we go along. Okay, so now we're going to do some experiments here. Well, some that I've already previously done to see what happens. So I'm going to roll a pair of dice 50 times, then 100 times, then 500 times. Then I'll do it 1,000 times and compare those samples. Now, I didn't physically roll the dice 50 times. I did a computer simulation. It was a lot quicker than physically rolling the dice. But 50 times, this is what happened. So up the top, I've got our census. So down below, frequency. There's the experimental data, if you like. Oh, I just noticed I've labelled that row wrong. See, I've written it as x squared px like the top. That should have been x squared times relative frequency, of course, for that one, because that's a sample rather than a census. So you can see the expected value of our sample there is 6.4, just using that data. So it's not the 7 that we know if we had the population it would be. So it's close. The difference between then the population mean and my sample mean was about 0.58. The variance of my sample is 5.8036. So the difference between the population standard deviation and the sample standard deviation was actually 0.0061. So it was actually quite close. If I was to add my sample on top of that population graph that I drew before, you can see, so the blue, what are they? Well, asterisks or whatever they are. They're the sample data spots where it fell. So it's not quite the exact census that we know, a little bit different. The theory being, we said that the more times we do it, the closer it should look like the actual thing. So 100 times what happened? Well, now you can see that the expected value turned out to be 7.16. So the difference now was 0.16. Interestingly though, have a look at the variation, or the variance. 5.9544, so the deviation now is out by 0.0250, which actually is a bigger number. But we're just dealing with random numbers here. I mean, that can happen. There's the graph. Now, I don't know if you remember the last graph, but you can see it on your sheet. So you can see they're sort of coming closer to fit the data. All right, 500 times what happened? So when I ran it 500 times, the expected value came out to be 6.86. So now the difference is 0.14. The variance, it got bigger again, 0.0394. So there's the graph with the comparison, and it's getting closer and closer to forming that same graph. So then I went 1,000 times. 1,000 times, expected value became 7.042. So now it's only out by 0.042. The variance, 5.5382. So our deviation's out by 0.0619. But that graph, when you look at the graph now, that's getting pretty close. Yeah, the middle of the data is certainly higher, but other than that, it falls pretty close to the actual graph. So that's 1,000. I could have kept going, of course. So I could have done 10,000 next and so on and so on. But as I say, what we should find, if it was possible to do it an infinite number of times, we should get it matching the population on that one. Right, now, we're going to do 13D. You know, it's in 4 questions there. It's a little bit different, this exercise 13D, in that it's going to get you to sample. So I've picked 4 out.